All right, so if we're looking at a Y connected source, let's just create our own little Y connected source here. I like to draw it like this so that it actually looks like a Y. And let's just call this one A. We'll call this one B right here. And we'll call this one C. It probably makes more sense to put that there. And then let's move this thing down and over a little bit. And then this is my neutral N, right? And so this VA neutral here will often be something like 170 angle 0 degrees volts. VBN, which would be here. I guess I should just stick with my same coloring scheme, right? Let's make this one blue. For the green, or for the VBN, we'll do green. So VBN would be something like 170 angle minus 120 degrees volts, right? That's what we saw previously. I'll go back here. VBN is minus 120 degrees from VAN, right? You see that? And so the last one being VCN, which I'll have to do in red, is going to be here. And that's 170 angle plus 120 degrees, or you could write it as minus 240. Both are valid, okay? And so if we were to create these waveforms, of course, what we would see is we'd see three waveforms that are 120 degrees phase shifted from one another. It's not perfectly easy to draw these, but roughly something like this is what we would see, where we have 120 degrees between the blue and the green, 120 degrees between the red and the green, and then another 120 degrees between the blue and the red. And that is one full cycle, T, right? And so this is what we see when we look at line to neutral voltages. And the question is, what do we look at when we see line to line voltages? So what I'm going to do is I'm going to write these equations into the time domain for VA to neutral, VB to neutral, and VC to neutral. And then in the next slide, we have, I have this slide called line to line voltages. I'm going to derive the line to line voltages that we talked about previously. So first and foremost, I guess I don't need to write them in the time domain. I could really just do it in the phasor domain and convert to complex numbers. So why don't I just do that? So if I wanted to derive, coming back to the line voltages that we saw, let me see what's the best way to do this. Okay, I'll just draw them. We'll call this A. This can be B. It's kind of hard to draw these. Well, it's hard for me. I'm not a great artist. These are our three signals that come off of the delta. This one will be, what did I do? I did a dark blue here, VAB. And then the orange for VCA. And I did a green for VBC, which is this one. Okay, so those are our line to line voltages. But I want to show you how we get to those and why are they different from line to neutral voltages, okay? So let's start back here with VAN. And let's say that I wanted to take so right now I'm saying if I were to take my probes and I were to measure the voltage between VA and V neutral, I would measure 170 degree angle 0. I would measure this blue waveform right here. Well, what would happen if I took the probes and instead of putting my red probe, I guess I should probably draw some probes here. Let me go to a red. I draw my red probe on A, and I put my black probe on B, and I want to measure the voltage the voltage difference between those 2 points, right? Instead of doing it between A and neutral, I'm doing it between A and B. Well, what my reading would have to be is it would have to be the voltage difference between VA to neutral and VB to neutral, right? Or better yet, it's just the voltage difference between VA and VB, which is equivalent to the voltage difference between VA neutral and VB neutral. Why is that the case? That's because if I look at VA to neutral, what is VA to neutral? VA to neutral is the difference between VA and V neutral, right? So if I say VA, oops, sorry, my pen malfunctioned. VA minus V neutral minus VB minus V neutral, I get a negative V neutral and a positive V neutral, and those just go away, right? So I can say that VA neutral minus VB neutral is equal to VA minus VB. Okay, well that's great, because that means that now I can look at VA neutral, which is 170 angle 0 degrees, and I can subtract VBN, which is 170 angle minus 120 degrees. I can convert both of these into rectangular, and from there I can calculate the difference and go back to phasor, and I'll get my phasor for VAB, right? Because if I'm looking at VA minus VB, this is equal to VAB, which is what I'm looking for over here. I'm interested in knowing what is this voltage here, VAB, my line-to-line voltage. Again, I'm going to label these. This is A, B, and C. This is VAB, this is VBC, and this is VCA. Okay, so let's go ahead and carry that out. If I were to put 170 angle 0, let me just write here again that this is VA minus VB. 170 angle 0 is just 170 plus J0, right? Minus, and let me go ahead and do this in my calculator. It's going to be 170 times the cosine of negative 120, and then 170 times the sine of negative 120, and it comes out to negative 85 minus J 147.22. Okay, so I add these up, and what do I get? Well, 170 minus negative 85 is 255. And J0 plus J147.22 gives me a plus J147.22. And I can go ahead and convert this back to, let me just write it out, plus J147.22. And I convert this to a phasor, and I get that VA minus VB, which is VAB, is equal to 294.45, angle 30 degrees. And so there you go. VAB is a larger magnitude, a significantly larger magnitude than 170, right? My original signals are 170 volt amplitude, so like right here. And not only is my signal much larger, it's also phase shifted by 30 degrees from VA. It is 30 degrees shifted. Let me erase this value here. Okay, and so it actually turns out if I multiply 170 divided by, or sorry, 170 multiplied by the square root of 3, what does that give me? It gives me 294.44. Okay, and that right there is exactly what I just got, or 294.45. So it just so happens that if you do the trig, which I haven't done here, but I'll do it in the next video, we will prove that the line to line voltages, which are these ones, are actually √3 times larger than the line to neutral voltages for any given system for the same amplitude of these sources. So if I take the A and the B, and that's where I'm measuring from, instead of measuring from A to neutral, I'm going to get a signal that's √3 larger and shifted by 30 degrees. Okay, and I'm going to show this in SPICE as well, because I think that the math can make it a little bit confusing. But hopefully the takeaway from this video is that line to neutral voltages, we're measuring from the line itself, A, to the neutral point. And so whatever that value is, you know, it depends on the sources that are here. And then if we're looking at line to line voltages, even though they're represented this way, it's these sources for the same magnitude here, right, 170, they would give me a value that it's √3 times larger than the equivalent line to neutral voltage, okay? Hopefully that's not too confusing. I think I'm starting to just say too many things and I don't want to confuse anybody. So I'm going to just go ahead and stop this video here. And in the next video, I'm going to show the proof that the line to line voltages are √3 times larger than the line to neutral voltages, okay? So I'm going to go ahead and end this video.